Hello, hello, hello. So we are going through one of these instructional problems today. This is number 47 from chapter 9. I've modified this a little bit. You can always look at the original, though, in the back of the chapter. So we have a 1.5 kilogram ball that is shot straight up. It's initially with 200 joules of energy. So what forces are present on this ball after it has been shot straight up? The big thing here is that it's after it has been shot straight up, so I'm considering no effects of actually shooting it. It's just in the air. If I think about it that way, this is almost like a kinematics problem. It's just under the force, under the acceleration of gravity. So force of gravity is the only thing working on this right now, right? So gravity is it. There's no surface for friction to be there. There's no surface for normal force, no strings for tension. So we're just with gravity. So easy part A. Part B, what's the sign, positive or negative, of the work done by gravity as the ball flies up? Explain. So let's just think about the work for a second. Work is equal to F dot it with our displacement. I'm going to write that as delta x, even though we are going to be moving straight up. Maybe delta y is more appropriate. I'm going to use delta x more generally, though. We can rewrite this using our dot product as F dot the magnitude of F dot it magnitude of F multiplied by the magnitude of the displacement times cosine of the angle between there. Alright, so if I think about this ball, it is moving straight up. This is not a free body diagram, this is just a quick sketch. I have a displacement vector going up. I have my force of gravity going down. What's the angle between there? It's 180 degrees. So when I'm thinking about the cosine here, of the angle, I'm thinking about cosine of 180 degrees, cosine of 180, that's negative 1. So what is the sign of the work done by gravity as the ball flies up? The work is negative, since the force of gravity opposes, how about that? Opposes the displacement. So what we're saying is the work done by gravity here is actually taking energy out of our system and putting it into the environment. How much kinetic energy does the ball have at the top of its trajectory? Explain. So kinetic energy, we've said before, we'll say again, kinetic energy is 1/2 mv squared. If I'm thinking about this ball initially, it goes up, it comes back down, right? It goes up, comes back down. I have some initial kinetic energy, some final kinetic energy, and then I also have some kinetic energy at the top here that I can quantify, right? What is that? Well, I can simply look at my expression for kinetic energy, 1/2 mv squared. I know the mass. I know the mass throughout this entire situation. What is the velocity right at the top? Well, the velocity right at the top is 0. So the kinetic energy at the top is a big old goose egg. It's 0, right? 0 joules. And we can say that the kinetic energy at top is 0 since the velocity is 0 at the top of the trajectory of the trajectory. Another way of saying this is I'm not moving, right? I'm just not moving. If I'm not moving, I have no kinetic energy. Cool. Does the work kinetic energy theorem, using the work kinetic energy theorem, and we've listed that here, the external work is equal to the change in kinetic energy. How high up does the ball reach during its flight? So we're kind of taking this scenario that we talked about in part C here and splitting it in half. We're saying that I have an initial kinetic energy here, I have a final kinetic energy here, and I'm just going straight up. So the change in kinetic energy, right, I know that my final equals 0. What's my initial? Well, my initial is probably just the 200 joules of energy at the top, or sorry, at the top of the page, at the beginning, because it's moving, right? It's moving. That's probably all the energy is kinetic. Final minus initial gives me a delta KE of negative 200 joules. If I think about the work external, that is my force, mg, times my displacement, delta x, times cosine at the angle between them, which we said was 180 degrees. Set those equal to each other. And this is just a negative 1, so I'm going to get rid of the negative and the negative here. And I have delta x then equals 200 joules divided by mg, 1.5 kilograms times 9.8 meters per second squared. When I calculate that out, I get a number of 13.6 meters into the air. So we can use work to talk about how kinetic energy is taken out of the system and over what displacement that actually happens. We're going to see in Chapter 10 that we can talk about this in a very similar way with potential energy. The idea here is that gravity isn't taking energy out of the system, but rather gravity is storing it in the interaction between the Earth and this ball as it gets higher and higher from the surface of the Earth. But that's Chapter 10. That's going to be next week. We're not worrying about that right now. E. As the ball comes back down, how much work does gravity do on the ball? What sign is the work done by gravity? Let's answer this second part first. What sign is the work done by gravity? If I'm thinking about the ball coming back down now, delta x that way, and my force of gravity down, the angle between these two vectors is 0. If the angle between these two vectors is 0, cosine of 0 is 1, specifically positive 1, and so my work done by gravity is positive. So now we can say how much work does gravity actually do on the ball? Well, assuming it travels the same displacement, right, and ends up exactly where it initially started from, delta x stays the same. It's 13.6 meters, right? And so the work done externally to begin with is mirrored, right? The work done externally up should equal the work done externally down. What we're saying is that the work done by gravity is 200 joules. Now, it's positive 200 joules. I guess we really should say that. We're saying that this is a negative here. If this is up, this is down. Only because, right, we now have our force in the same direction as our displacement. What's the final kinetic energy of the system as it reaches the initial starting point? Well, again, change in kinetic energy equals work done externally. But now we're saying it's down, right? We said that the work done external is 200 joules. change in kinetic energy should be 200 joules, final minus initial. Well, initial, right, is actually at the top here now. We're saying that we have 0 energy here, then we just drop down. Our final kinetic energy, it's really messy. Our final kinetic energy should be, right, should be the work done externally, which is 200 joules. So it's mirroring things, right? What goes up comes down. We saw this in kinematics. If you calculate it, the initial speed versus final speed of a ball thrown straight up and caught at the same level, you'll find that those velocities are the same. And so that's actually our next question. What's the initial and final speeds of the ball? What we're saying here, of course, is that initial equals the final speed. And now I can actually plug 200 joules into our 1/2 mv squared equation. If I throw 1/2 on the other side, I get 400 joules divided by my mass, 1.5 kilograms. Let's throw that all under a square root. That would give me my velocity. When I calculate my velocity, I get 16.3 meters per second, which is pretty reasonable. All right, 2 more. What if the ball was now shot up with 400 joules of kinetic energy? How high does the ball reach now? So what we could do is actually just look back at part C here, or I guess it's part D, and recalculate things. I would prefer to look at the conceptual relationship found in our equations, right? We have the change in kinetic energy equals mg delta x times cosine 180 degrees, but we know that that cancels out. So what I'm saying is, what if I double this? What if I double my kinetic energy? Well, if I double this, what has to change over here? The mass can't change, right? This changes. My displacement changes. So if I double my kinetic energy, I double the distance that I actually go up, right? So 400 joules should give me a 2 times delta x of the 200 joule height, right? And which we said was 13.6 meters. So that gives us what? 27.2 meters in height. You could recalculate this if you want, but this is almost a conceptual kind of problem of seeing if I double this, what happens to this. And then finally, how much more is the ball's initial velocity if the 400 joule scenario, in the 400 joule scenario compared to the 200 joule scenario. So again, you can recalculate pretty easily. I want to just take a look at this. If I think about my kinetic energy, I'm going to double that. How does that change my velocity? Well, it's not a one-to-one, right? Doubling kinetic energy doesn't just double my velocity, because I got this square here, right? I got this exponent. So maybe it would be better to say 400. Let's look at a ratio here, right? Because actually that's what it's asking us. How much more is the ball's initial velocity? So 400 joules over 200 joules, and we'll set up the same ratio on the other side. 1/2 mv do v1, no, v4, 400 squared over 1/2 mv 200 squared. So this is going to be 2 on this side. 1/2 m's cancel. Throw that up on the other side. I'm going to get left with 2 v 200 squared equals v 400 squared. Of course, taking a square root, right? I get a square root of 2 times my initial v. That is equal to my new v, right? So the square root, So square root of 2 times more than before. If we actually wanted to calculate that, 16.3 times the square root of 2, I get V400 is 23.05, so I'll just put 0.05 meters per second. So that is number 47 modified. If you have any questions, please let me know. Otherwise, I'll see you around.